as usual, I'm gonna figure out what I'm gonna do today, but last week I ran into a unfortunate setback with my entire approach for implementing guard pages for my kernel threads. And I will tell the entire story of how that happened. At least, yeah, the approach I was going for seemed really good. And then last week we discovered some flaws in it. And so that made it not as trivially easy or not as obviously a good solution as I thought it would be. So we're going to regroup, and there's definitely still a way forward, but I'll just need to see which of the options I'm going to go with. So that's a bit of the news for today. And I'll just make sure everything sort of went okay with the launching of the stream. And we will slowly get into things. Assassins, bye. Let's go. Hello. What's up, Lane? We are live. Yeah. Yeah, Assassins by and Lane get points. Drew, what's up, Drew? Y'all are the first 3 people in the chat. Awesome. Smash a couple hearts. Hundos. Thank you for joining the chat. Yeah, so the way it's gonna work today, I'm gonna start off by telling you a bit of a story and catching you up. I know it's been kind of difficult to follow the last couple weeks of development, especially if you haven't been tuned in the whole time. So I'm just going to do a bit of a storytelling and try to go through a bit of what's been going on and recap the journey of the stack guard pages and why it's been taking so long. I really did not want guard pages to take like 4 or 5 weeks or more like it's been doing. But here we are. That's how it has played out. So recap story of guard pages, what happened and what we'll do today and going forward. Afnan, what's up? Test 2, perfect. I feel like they updated chat widget because I feel like it updates a lot faster than it used to take several minutes for the first message to pop in. Drew says, it's my first time watching your content. Can you please share a bit of history about this project of yours? Yeah, totally. I can. That's a good idea. It's a good idea. Yeah. Yeah, I can absolutely start with a bit of a high-level recap, and then we'll get into the more specifics. Wow, this is what the project looks like. From a certain perspective, this is over 2 years of weekly operating system development going back to February 2024. And we are working our way over in this part of the jungle. Yeah, so basically, so what's going on here? I've been working on an operating system for 2 years, and there is some nuance to that. Really, I'm trying to just learn about OS development, kernel development, that kind of stuff. What's been going on is for the first over a year, I was following this MIT course, MIT 6828 2018. And I live streamed myself doing all of the projects for this MIT coursework. And that was the first over a year of me streaming, was publicly doing the projects, the labs, the exercises for that course, and working on this microkernel that they use for the course. And at some point I finished the course and it was time to actually start my own OS. So then I spent quite a bit of time developing infrastructure. And my own OS has a couple key principles in mind of modern C++, being one of them. And I want to use a lot of third-party libraries for basic data structures. I do not want to implement my own linked lists, for example. So I want to be able to use third-party libraries. And I'm doing this more in the embedded style, not really desktop operating system style, more like embedded real-time operating system style of OS development, which means more static memory allocation as opposed to dynamic memory allocation. And so I would say probably in late last year, I finished all the key infrastructure and we've actually started building the kernel. And we're tackling the most important parts, which brings us to guard pages. So guard pages are a safety mechanism that kernels use to prevent memory corruption in case of a stack overflow. And the way guard page works is, drawn this diagram like many times, but you have memory. Let's say you have a stack, your stack in memory, and at some point you're going to have a stack pointer that points, it's going to point down here. And then at some point, it's possible that actually you do too many function calls, you do too many local variables, and your stack pointer goes beyond the boundary of the lower bounds of the stack memory that was allocated for the stack. And it will start to write and read beyond that. And the goal with the guard page is to make sure that if this ever happens, this is caught with a page fault where the kernel can crash or make it very clear and obvious that a stack overflow happened. Because the last thing you want to happen is have silent memory corruption when the kernel overflows one of its task stacks and then keeps running. That's really bad. And so that's the general principle. And I've been trying to work on this for a long time. And the general way the story goes is in the initial V0 of this, I had tasks, but and they had stacks, but the stacks were in the phys map, and so they were in this region of virtual memory where all of physical memory is mapped. And there's a lot of downsides to using that. It's very easy to use, but there's no memory protections available because the entire region is readable and writable. And so it's trivially easy to overflow a stack in the phys map and corrupt memory below it. And so they were in the phys map and had no guard pages. So this was like the initial prototype of scheduling and tasks. And then the idea is we want to do two things. One, we want to allocate the stacks not in the phys map, but rather in the kernel virtual memory area. And so if this is memory, maybe I'll just do this. Let's pretend this is just all of virtual memory. So on x64, the kernel has the way it sort of works is the kernel has the higher half of the 64-bit address space. I think it's about 120 terabytes in each half. And so we're mostly focused on the top half. And the kernel, the phys map is in some region here. That's present. The only other mapping we really have is the kernel itself is mapped in the top 2 gigabytes. And the idea is to use the rest of this space, sort of, what's represented by this section. And you can map things in there. And so that's the idea. That's what I mean by rather in kernel virtual memory. Everything basically outside of the phys map, all this stuff is eligible space to be used for kernel virtual memory. This is where the kernel actual binary sits. And in a traditional kernel, you would then make more mappings in this area. But from my approach, it's a little bit of bit of a different approach because I'm using the embedded style or more like static allocation style. So I'm actually statically allocating objects into the kernel binary itself, which sort of blows up the size of the kernel. And so, so in practice, my allocations are sort of ending up all in this zone, but that's okay because this counts as kernel virtual memory also. So basically just like, yeah, anything outside the phys map counts as this area basically. These are all eligible spaces to allocate the stacks. And yeah. Drew, is it going to be a GUI-based OS? That is very unclear at this point what a GUI would look like or how it would work. All I can really say is that a GUI is very, it's down prioritized. It's not my main focus. So Pyro SP, ESP. Salute to you too. Yes. All right, let's continue the story. So we have this V0. Now V1 we want to allocate the stacks rather in the kernel virtual memory. We also want guard pages, and so we want to have something like this initial diagram, right? And I've tried different approaches to doing this, and I will quickly go over to the code to try to find. Okay. So you can see here a variety of approaches I've taken for this. And to briefly explain the way things work, and so there's tasks and then there's task stacks. And so over here I have a task list of stacks, and this is basically, it's a container of a fixed number of tasks. Currently it's 4, which is an embarrassingly small number, but the idea is to make that a lot bigger once this works. And so I have 4 tasks that can run on the system, and a task has some state, and that's what's stored in this. It's basically this container of 4 things, and there's a linked list that links them. And in a very simple world, ideally, like every task needs to have a stack. So ideally, I would also just be able to allocate. So over here, now here's basically the struct. Ideally, I would have a task stack or something like stack and just declare it in line in the struct. But that very ideal, very naive solution just simply does not work. A task stack, as I'm doing it, is a large allocation. It's like 8,000 bytes because I want to have a guard page and also a stack. And ideally, it's going to be even more. And so that's not really something that we can just put into the task struct in line. There are just so many problems with that. And I mean, alignment is simply one of them. It's like we have like 4 variables and then 8,000 bytes. That's not going to work. So what we want to have, and so this is the trivially broken or like trivially not working solution. And so what we really want to have, and so rather than having these 4 members and then the stack in here, what we want to have is that we want to have a nice contiguous compact storage of these first 4 things, but then over somewhere else in memory, we want to have 4 stacks. And these are each like 8K or more, and they're all contiguously packed against each other. And then the idea is that when we're allocating tasks, they can then get a stack to use. And so this is not working. The next evolution of this, we want separate contiguous storage of stacks. And this is really the question of how to do this. This is what we've been diving into. How exactly do we declare a separate set of stacks in a way that can be used and sort of linked with their corresponding task. And there are at least maybe 2 or 3 possibilities, and I've been exploring all of them. So the first option was trying to use, right, how do we do this? So the first option, option 1, use an ETL pool of stacks. So ETL pool is a data structure we have available to us. It's a pool. A pool is perfect for having contiguous objects that are contiguous in memory together. And it even has the semantics we want of being able to allocate and deallocate from the pool. So it was a very promising candidate when I first started trying it. And the way it sort of looks is that in the create task API, when we go to create a task on the system, we first allocate something out of the pool, and then the task itself can store a pointer to its task stack. So that was sort of the idea. Like, these things are stored in an ETL pool. And the reason this broke, the reason this was not actually a viable solution, is we have a specific need here. And I'll actually take a quick break for the Palmtree timer. Be right back. Feel free to join me for a stretch. So we have this sort of interesting property, or it's not exactly a property. We have a need for these things in that we want to unmap basically the guard page from each of these things. And that's how the guard page works. And that's why this breaks. This is broken because we want to unmap the guard page, but ETL stores a free list inline inside unused objects. And so internally, the pool uses a linked list, a free list, to link things. And it stores that metadata in the early bytes, the early part of the object, the unused object. And this does not work if we're unmapping it from the address space. And so the option 2 was, okay, we're going to have a custom pool which stores the metadata out of line, because that was the problem. The metadata is stored in line inside these objects. And so the other solution is, it sort of looks like over here. We have all our stacks over here, and then we keep some metadata off to the side about which is used and which is not. And this is what is known as our bitmap pool. It's a pool that uses an out-of-line bitmap off to the side that stores the information about which of these stacks is in use or not. And then, but why is this broken? So this was very promising, and it only started to break very late in the process once I realized a few things. So broken, it's not broken, but doesn't work, or challenges. So one of the challenges, we want to have a smart pointer to a task stack. That is something I want to have. And so that's what I had. When we originally were prototyping something, or how the task, when I was originally prototyping this, and by that I mean I was originally prototyping it here. In my prototype, the task stores a smart pointer to a task stack, which is nice because then the stack gets automatically freed from this pool when the corresponding task gets destroyed. And so When this thing gets destroyed, this thing automatically gets released back to the pool. That's a really nice use of smart pointers as opposed to manually needing to free this memory. So it's something I wanted to have in my task. And so that's where the problem started. Because the way the smart pointer works is it was relying on a specific feature of the ETL pool called the I pool. In V1, we prototyped with ETL pool relying on I pool. I pool it's sort of like a type erased pointer. It's like a type erased type which can reference a pool of any size because these pools are statically allocated. They have a size template parameter. And that's really cumbersome. We want to be able to reference pools in a more generic way in this custom smart pointer. And so we were relying on this iPool concept. The problem our custom bitmap pool does not have the iPool concept. And last week we looked into what would it take to implement an equivalent of the iPool for our custom pool. And that's what we were looking into last week. How do we type erase this thing and type erase away the size template parameter? And this is not really a fundamental limitation, but the very concrete challenge that sort of roadblocked that line of work is to implement the type erased version of the object. You basically need to store pointers. You need to, rather than having like a static array, you store a pointer and then a size, and then you operate solely on the pointer and the size to implement the data structure. And this works for iPool, but the problem with bitmap pool is that to actually implement the bitmap pool, you need to have a few things. So right, you need to have a pointer to the start of the array, basically. I was prototyping it as an array as the backend storage. You need to have a size. I'll just call it to start of data. Then you need to have a size. And then that's basically the same thing as the iPool. But then the tricky thing is the bit set. We also need to have sort of like this dynamic bit set. And we need to have a bit set implementation that operates dynamically on a bit set of unknown size. And this is the concrete roadblock. I simply do not have a bit set implementation that works this way. The only bit set implementations I have are like statically sized, where you need to pass a template parameter for the size. So I don't have a dynamic bit, need a dynamic bit set. Basically, I'm gonna make this red because that's really the key point. In order to do this type erased thing, you need to have a dynamic bitmap. I currently do not have one. I could write one, but that's basically a red flag to be a stopping point before I go ahead and dive into that whole approach. That is sort of a red flag. And yeah, that's what we're doing now. And so it's to implement it, we need a dynamic bit set. Currently don't have one. Could write one, but let's pause for a moment and just consider our options. And so these are the two broken approaches that I've been prototyping for the last probably over a month. And I'll mark them as red to show that they're kind of broken. And that's the current state of understanding. And now the question is, how do we continue? Let me check the chat. Thank you, Sunlaser, for subscribing. What's up, Product Design KF? Do you have a computer science degree? I have a computer engineering degree. What's up, ML? Where are you stuck? We're on Linux and modify it. Working on it as open source. Yeah, I'm stuck on exactly this. I mean, I'm not exactly stuck. I have some ideas, but this is the current challenge. How to implement our stack guards in a nice way. What's up, Margin? Great day. Appreciate it. We need a person like you. Really consistent, so I appreciate you again. I appreciate you, Margin. Thank you for watching. So let's talk about solutions. I think it's always important to spend a little bit of time considering a design space of a set of solutions as opposed to just blindly jumping in and pursuing the first thing that works, because it's easy to be surprised by elegant solutions that exist that were not immediately obvious. Yo, Digitalized, what is up, man? Nice to see you. Thanks for popping in the stream. Yeah, so let's talk about solutions. And so we have our two broken approaches, and I think I was even sort of doing it last week, but how can we move forward from here? I'll just write that down. How do we move forward from here? What are the options? And I will just sort of brain dump a little bit. So 1, proceed with. Number 2, implement the dynamic bit set. So this is just sort of being stubbornly following the 2 approach and just pushing through. And the key point is needing that dynamic bit set. And just to brain dump, so maybe 2. Don't use a pool for the stacks at all. So what do I mean by this? So the idea behind this idea is instead of having a pool of tasks and then a pool of task stacks where sort of like maybe we allocate this thing, and then maybe we allocate a task stack into points over here. What if we just have a system where we allocate a task, and based off of its index number, it just automatically finds the matching task stack? The key problem is that currently not possible to get the index of a task. That is not exposed by the ETL list container. The ETL list container, the list, it's over here. So it's this mtasks thing. So, and weirdly, my definition isn't not working, but so if you think about a linked list data structure, the operations on a linked list are sort of like add to the end, insert on the end, insert in the start, remove from the middle. Getting the index of an item in a linked list is not really something that's super commonly done. Primarily, at least for one reason, because it's very expensive to compute it. With a linked list, I mean, either every node stores its index, which consumes space in the node and also is extra metadata for bookkeeping, which is kind of annoying to keep consistent. If you don't store the data in the node, you need to find it dynamically by iterating the list. And iterating linked lists is extremely slow in the general case. Oh, is my voice not coming? Wait, what? All right, chat, I need you to tell me if Averald Weavadi is capping or not. What's up with Vedant? On my side, it seems like the audio is coming through, so I would appreciate just double check on that. All right, thanks. Visualized. Word. All right, what's up, NSG? So yeah, basically the idea is like in general, getting the index of an element in a linked list is not exactly a first-class operation that is really supported on linked lists. It's a bit of like an odd thing to do, but that's sort of what we would want here. It would be so simple. It would really simplify things if we could just allocate a task stack, get its index, and then simply start using the stack at the other appropriate index. This has significant simplifications. Many pros. Very simple, no need for allocation or deallocation of task stacks. No need for a smart pointer because there's no allocation happening. And it's frankly just like a really awesome solution. And the big roadmap is that it's just simply not possible to get the current index. And so we would need to patch ETL or do an out of line external sketchy hack. And the only reason we might be able to hack this is because we're not using a normal linked list. We're using an ETL static list, which means all of the nodes are allocated statically up front and are allocated in a compact way. And so it is technically possible if you have a pointer to the start of the list, which is like over here, and a pointer to a node, which you get from which you can get from mplace back or whatever, then technically you could do a subtraction and find out the index with the one caveat of you need to know the size of each of these things. And it is not necessarily the size of your object being stored because that is an implementation detail of ETL, and it can choose to pad things as it likes. And so you don't actually know. So you either need to make some guesses or hard code something or read something in order to actually do this externally. But it is an option. And that's what I mean. That's what I mean here. You can do an out of line external sketchy hack to add some kind of API for getting the index of an element in a static list. Or we could just patch ETL, which is less sketchy because then we can make use of the internal node structs and stuff like this. But that has the downside of patching ETL. And in general, it's nice to not patch the hell out of your dependencies. Like patching things makes upgrading much more difficult potentially. It gets you away from mainline dependency, and you start to slowly fork your own thing. And so that is one downside of patching ETL, which is one of the main reasons I've been avoiding this and have been trying as hard as I can to use different approaches that do not require patching the library. But this is just not really working out, and frankly, I don't love this idea of the dynamic bit set. So we currently only have static bit sets like frig and ETL. Maybe even have the standard bit set actually. Bit set. Yeah, I think we even have standard bit set. So I have like okay, I wish I could browse this a bit more easily, but it's not really that important. But patching ETL is calling to you like the Green Goblin mask. Yeah. And so unfortunately I have 3 static bit sets, but no dynamic bit set. And that is just making this annoying. And really what I would want to do, frig bit set, like, so this is frig's bit set, it's a static one. What I would really want to do is have some kind of like it would basically, I would want to have it be in frig, I think. I would probably end up patching frig. Maybe even I would want to upstream that. But it would basically be, instead of having a bit set with this size parameter, this size template parameter, where we have this n that's like used, let's even see, like used ostensibly like all throughout the implementation. It's kind of hard to grab. All right, quick stretch break. Be right back. All right. So we can see that this n is sort of proliferated all sorts all throughout the implementation. Instead of doing that, basically, we're just going to have an I bit set that is going to have like a member variable for the size. And in every location, we need 2 things. We need a pointer to the start of the bit set buffer and then the n. And then this entire implementation gets kind of transformed to be in terms of this pointer to the start of an arbitrarily long bit set and this member that controls how long it is. And visualize the reason we need a dynamic bit set goes back to the problems we were having last stream. It's sort of this whole chain of events. It's like, okay, we had the bitmap pool with out of line metadata. So that's the whole idea. We had this awesome bitmap pool. It's this pool data structure that has all the objects right there, and then off to the side this little bit set. And that was so freaking cool, and I was so happy with it. The challenge was we want to have a smart pointer to a task stack. So sort of like over here, we can see that in the task struct, the task has a smart pointer to a task stack, so it can automatically free it. What's up, Apnobenzene? Yes, man, you're exactly 44 minutes late, but it's all good. So we want to have the smart pointer, and that's where we get into a couple of problems, because with the smart pointer that I prototyped for iPool, I was relying on this iPool type. A task stack unique pointer. this iPool type, which allows the smart pointer to be used for a pool of any size. And that was great. That was really easy. The problem was that the custom bitmap pool that we implemented doesn't have a version of this iPool concept that was so useful for creating the smart pointer. And so last week we tried to implement this. And that is the part that needs the dynamic bit set, because to implement this iPool concept, the iPool is like this, it's called type erasure, where we have this pool, but it has the main problem with the pool and a lot of the other ETL structures is you need, like in the ETL list and even the main problem is that you need to specify the size as a template parameter. And so that's baked into the type signature of this type. And that's the normal pool. And the iPool is a way, it's sort of like this type that erases that size, and it operates on arbitrary sized pools, which is very, very useful. And so that's sort of the idea. To implement the type erased type, you basically you store pointers and a size to the data, which is of unknown size. That's the whole idea. It's like the pool has a static size that it's like hard coded into the type with that n we were seeing everywhere. The iPool is dynamic and operates on arbitrary sized things. So I know it's kind of sort of complicated. I hope that this helps a little bit. But then the tricky thing is to implement the type erased bitmap pool. We have the pointer to the start of the actual data and then the size for that. But then we also need to have the same thing true for the bit set, which is a dynamic bit set, where we have this thing that operates on a bit set of sort of dynamic size that is unknown at compile time. And so that's sort of the whole thing behind that. I think one other option that I didn't quite say here is a lot of the problems I was experiencing are based off of the fact that the task stack pool is has a size template parameter. Right, it has the std size T for static allocation. So we want like a SLL for the bit sets. What is SLL? You signed long? I actually don't quite understand your message, Digitalize. But mainly, really just the key point is we don't want, I think that the frig bit set really just makes it kind of clear. We do not want this template parameter with the size T. Okay, singly linked list. Yeah, it's like it's not really like a linked list, but just the point is, like, I think it's sort of like right here, like the size is just hard coded into this type. Like the n is used to compute the number of bytes stored in this, like, basically int buffer, right? It's like a fixed size int buffer. And therefore, like, you could imagine a version of this class that took a pointer to a bitset start, or maybe even buffer start, and then a size T length, or maybe even num bits. That's really That's sort of the concept. And you don't want this compile time template at type of n. The idea is to be able to write the idea is to be able to write code that can operate on any kind of bit set that you pass to it. Like you can imagine like helper function, even, let's just imagine we didn't have the I bit set. We wanted to write a helper function that sets the 100th bit or something weird. What do we type here? Bit set. We would love to just type like bit set, like set on, right? We would love to just do that, and we cannot do that because bit set requires you need to pass a number there. Some overall interface that doesn't care about the templated non-type. Yeah, I think that's exactly it. So basically, we would absolutely love to have like this bit set that just simply does not work because we need to have a number here. And so the idea is to have some other type called the I bit set, which allows you to do this. And it can take any kind of bit set you pass to it. And it doesn't hard code some specific bit set size of like a 200 bit set or like, something like that. And that is the motivation behind the type erased type. And at a conceptual level, this is what the I bit set looks like, where it's like, yeah, Matias, yeah, this is like totally just like example code. Although actually it's actually not an interface. I think that's sort of a bit of a confusing point. It's just I don't know why it's called I. ETL names, it's like pool and I pool. The I is more just to represent that it is kind of an interface, but it's not the classic like OOP sort of interface. It's only an interface in the most general sense that it operates on possibly different things. Yeah, it's a little bit confusing. It's like a little bit of both, but this is more like pseudocode, but I'm just trying to sort of make it like more clear, like the motivation behind the type erased type. So hopefully I'll just screenshot that in case we need to reference it again. But really there's actually a third option, and just for completeness, I'll write it out. Don't make task stack pool a templated type. And so my original idea was, also I think I missed some chat messages. What's up, someone? Their GitHub repo. Unfortunately, not currently. It's just my private project. Yeah. How's the UI? There's no UI at the moment. We're working on the core plumbing. So yeah. Let me see how. So basically the idea. So this is the third solution. It's a little bit more. It's a bit of a different kind of solution. And so a lot of our problems stem from this. This is sort of the ideal thing. I was trying to make the task stack pool also quite generic. And so the task stack pool doesn't make assumptions about how big it is. It similarly makes itself generic and offers a template parameter. And that's the part where this part would get difficult. Task unique. Yeah, task unique. So here is exactly the problem. And this is what we were looking at last time. So here's what I tried to do. I tried to implement the unique pointer. And the problem is that there's this size template, which means this whole thing needs to become a template, which means like the template argument spreads like a virus through absolutely everything. And that is a bad thing. And so that is why in these situations you reach for type erasure to prevent this massive proliferation of everything becoming a template. And this is exactly illustrating what I want. What I wanted to happen is like, rather than having this be a template and then needing to pass it into here, it would be so cool to just have this I pool thing. And then this is no longer a template. The problem is that this is hard to do. So Matias, yeah, so Matias is saying, yeah, why don't you just implement an interface? And this is totally an option, but the problem is you just need to do this. The problem is then you need to implement. Well, actually, yeah. What is the? Let me make sure I understand this. So Matias is saying, why don't you just make the bit set inherit from some interface and call through that. That's actually a reasonable suggestion. And that's actually different from what I was thinking. So that's genuinely a new suggestion. So I was sort of thinking that I need to go and have this class, so Matias is saying basically you need to do this. I bit set. Right, so this thing becomes an I bit set, and then what we would do in the bitmap pool is it would be here. So in our bitmap allocator, we would no longer store a bit set directly in the bitmap allocator. And let's just think this through, just for reference. Here's the architecture. No. Here's the architecture. So, and even to be more complete, rig bit set. So frig bit set is like the really super low level bit set type. I wrap it in a thing called bitmap allocator to give it allocator semantics, where you can alloc and free from the bit set. And this takes a size, and because they all take a size. And so what Matias is saying, let me make sure, yeah, yes, every bit set must implement the same functions for the vtable, yeah, right. And so Matias is saying, okay, so let's change it like this. Let's take the bit set and we'll make one change to make the bit set inherit from an I bit set interface. So we'll seriously introduce the idea of an I bit set. And then the corresponding change is that the I bitmap allocator no longer stores a bit set internally. It's going to do something like this. something like this. You know, this doesn't exist yet, but that is, yeah. And so that means the Bitmap allocator is more of like a wrapper rather than a thing that has a bit set. And what Matias is saying is that the nice thing about this is that none of these call sites change. We'll need to pass in a bit set over here. That's possible. And let's see, the trade-off with this approach. I mean, I want to say this is genuinely a good alternative to consider. I think it does actually solve some of the problems, and so it's sort of I was talking about a dynamic bit set more in the tradition of the iPool style thing. Matias is going a little bit different, and it's like a bit set interface sort of thing. The trade-off is that with the trade-off with this as an interface is that all of these become vtable calls. And so that is the trade-off. Matias, I think you would probably agree with that, right? That any an operation that is usually like super fast to scan for bits and stuff now has 2 vtable calls. One. So for example, let's say we want to allocate here. We're just trying to allocate a simple bit from the bitmap. Previously, it just had all the bits. It linear scans using like linear scans using this super fast built-in, and then it just marks it as used, which is just setting a bit. And I'm not saying it's bad. I'm not saying we shouldn't do it, but I'm saying it's a trade-off. Now this and this, so this find first set and this dot set become vtable calls, which makes it a lot more expensive. It, I don't know, probably like at least 1 order of magnitude slower. So let's stretch for 20 seconds. Be right back. Yep. All right. So that's actually, so I'm just going to take a moment to record that as a legitimate design option. So this is not something I considered. So we'll go with, call it option 0. Yo, what's up, Sensei? What's up, Ismail? Nice to see you guys. I was trying to find the... Oh, there it is. Okay. So this is Matias's idea. So don't store a bit set directly in bitmap allocator, rather introduce an ibitset concept. So to be very clear, this would allow us to it would solve a lot of the problems. Basically, things stop becoming template types. I just want to follow the full chain of this. So let's pretend that bitmap allocator, we did this change. So then bitmap allocator is used, so bitmap pool, right? So then bitmap pool no longer has this thing, but it gets a bitmap passed into it. And so bitmap pool doesn't have the template parameter anymore, which means that the task stack pool no longer has a size template parameter, which is exactly what we wanted. So that solves the problem. And we need to pass a bit set into the task stack pool to forward to the bitmap pool constructor, to forward to the bitmap allocator constructor. And therefore, and this is the whole point of what Matias was trying to say, if we don't have the size template parameter here, we can finally go to the task stack unique pool pointer, whatever, and it actually, it's not even a separate type. It's just simply this task stack pool natively does not have a template parameter, and that just works nicely. And so yeah, so that is the suggestion. That was to fully implement the chain, including the smart pointer. No need to write a dynamic bit set or transform frig bitset into a dynamic one, right? So that's a great plus. And I don't know if it's a con, but either we slightly patch frig to introduce this bit set, or maybe we add our own wrapper layer. So what I mean, and Matias, this is a slight complication that you wouldn't really have the context about, but the bit set is not first-party code. The bit set is a third-party library that I'm using. Block size. Why do you want to lose the template argument? Can you inline? So I'm trying to lose the template argument so I can write a smart pointer for the pool. And if I have a template argument, because in the smart pointer, I need to have a deleter that contains a pointer or reference to the actual pool. Kind of going back to your earlier question, do you have a heap? I do not have a heap because I'm trying to avoid heaps. I'm trying to do everything in terms of pools. I'm also trying to have no global state. And so for that reason, the smart pointer needs to store a pointer or reference to the actual pool so that the object can be freed from the correct pool. And that is where it becomes a problem to declare this pointer type. And that's why I don't want a template argument, because otherwise then this whole thing needs to get templated, and it's a huge mess. So, so we're getting close. this is actually a really great exercise in brainstorming different ways to solve problems. It really is. It shows you there's a lot of different ways we can solve this problem. And I think that's one thing I want to show, especially to more junior programmers or people that have a bit less experience with production systems. There are at least 4 different ways we could proceed here, each with their own pros and cons. And there's no best option. It's just the one that's correct given the set of pros and cons. And so the very slight problem with the frig thing is like, now we need to come over here and we need to sort of add like an I bit set, virtual, like, virtual destructor, virtual size t set. We're gonna have like this whole virtual boilerplate. This thing sort of becomes inherited from this thing, and so this is like a patch to frig. Maybe another way to do it is we could just make our own. I could make sort of my own bit set, and so using wait, what am I doing? Equals frig bit set, and so I could make my own bit set, and then I could have my own thing. And how would this even work actually though? Because so I was hoping to try to avoid the patch too much, but I don't know if I could do that. Virtual, we would have all the virtual boilerplate of all the methods, but the fundamental problem is that the bit set type here needs to at some point inherit from the I bit set, and the easiest way to do this is to patch frig. An alternative is to have my own bit set wrapper that truly is seriously just a wrapper. And every single method just forwards. You can imagine like doing this sort of thing for every single API that the bitset offers. And then we'd be able to do a bit set. And so this is sort of the alternate sketch at what this would look like. So as you can see, there are many different options. And I think this is such a good example of trade-offs and whatnot. So I want to, I want to thank Matias for that comment. And I think the most interesting piece here is that this actually seems like a good solution. This is not a ton of boilerplate. Lot to add to frig to restructure it in terms of dynamic bit set and the I bit set. This is almost certainly a smaller patch than this one would be. However, this is probably the smallest patch of all and has so many positives. It's really such a positive to if we go with this solution, it actually just structurally removes a lot of the problems. We don't have any need for a smart pointer anymore. We don't have any allocation or deallocation of the task stack. It really simplifies a lot of things. And so what I want to say is I think this solution is sort of like a local maximum that seems really good, but if we look a little bit around, I feel like this solution is actually really the best one. Just to try to explain this thing though. So the idea behind this is that, okay, we give up on the idea of making this a template type. And what we do is we take the constant from schedule to HPP, the knum tasks, and something like this. I mean, this is not how it would look, but conceptually, every time we would otherwise use a T size, we use knum tasks. And so we sacrifice the ability for this thing to be a reusable generic data structure. And we just say this thing is like directly tied to the number of tasks that are declared on the system. And that is just simply what it's going to be. Which is also not an awful solution necessarily. It's not like I really plan to have other clients of task stack pool. There really is going to be one instantiation of this task stack pool in the entire kernel, basically. But it adds an additional dependency on that one variable, which is sort of it just couples things slightly closer to the scheduler and just, yeah, sacrifices the ability for this to be a generic data structure. So, but just for completeness, that is the third option. Sacrifice ability for task stack pool to be generic. It becomes totally coupled to the knum tasks constant. And it similarly achieves the goal of removing the template argument, which was obstructing our smart pointer journey. And so if I were just to group these solutions, it's sort of like this cluster of solutions, and this is just sort of like a different world of solutions. I'll call this out as a negative. But this is also kind of a simple solution. But looking at the global landscape of these options, I feel like number 2 is probably what I want to go with. These are just such compelling pros, and the ETL patch is fairly minimal. And I am already patching ETL a little bit, and so it's not like a new patch. It's like it's like a patch. I've already have a few patches, and so that's kind of nice. As opposed, I have not really patched Frig yet, so that actually, I mean, I have a little bit, I guess, also for this find first bit thing. This option, while this is a really nice option, it is slightly more intrusive than I want to get into making this inherit from this whole thing. And I mean, just to be complete, adds vtable calls on every bitmap alloc free operation. Slow? I'm always very cautious to go with this like it's too slow thing, because that is so frequently reached for as a critique of things, but in so many cases, like it really doesn't matter. And so for me, this is not the primary objection to this design, but it's also not something just to totally ignore, because it does impact the performance of the bit set pretty considerably, I would have to imagine. So you're okay. What is up, vpool? Nice to see you. Thank you for joining. Can you run GTA 6? Not yet. And thank you, Abraham, for the sub. All right. Well, this was a very deep discussion stream so far. I'm glad we recorded all of this, because we can come back to the decision later and sort of see why. But for the moment, I'm going to make a executive call and say, let's try this. Also, I'm just kind of curious to do the ETL patch. So that is what we're going to do. So let's start to code. And this was just all kind of junk to clarify some points. None of it is real code, and I'm just going to delete everything. And so now let's make a little bit of a roadmap for how we're going to actually do this. And so so on a high level, declare the task stacks as an array, add a patch API to ETL for getting the index of an element in a linked list. Something like this. I think it's going to be pretty simple. So Lane is asking, as a fellow lover of C++, I find myself favoring Rust in my projects because of all the nice things it provides. What drew you to using C++? That's a great question. I'm using C++ for extremely practical reasons. I have significant professional experience with C++. I'm very, very comfortable with C++. I have basically no experience with Rust. And I wanted to keep things easy for myself and not learn OS development while also learning a new language, which is also reportedly sort of difficult, maybe with unsafe and the sort of things you might need to do in an operating system. So especially for a very beginner Rust programmer, I didn't think an OS would be a suitable project for me. And so C++ gives me everything I want. I'm super comfortable with it. It gets out of my way. And even beyond those, I am just personally curious to see what a kernel would look like in modern C++. So those are my specific reasons, but I'm so aware of how good Rust is, and I totally agree. And I'm using C++ for different reasons. So first step, let's get back to a place where we can even build the kernel. I have been stacking all these crazy layers of whip commits, and so even here's where I started working on prototyping the bitmap allocator and that like whole concept. But let's all take a quick stretch. let's just find any kind of starting point to here's where I was prototyping the initial broken approach with the ETL pool and the smart pointer. We can even go farther back in time, I think. But I may have added interesting. I wish I had time to clean up this history, but I didn't have any time at all this week. So okay, what should we do? Let's just find some reasonably like non-whip state. I think approximately here. I'm gonna make a new branch. Call it dev3 ETL patch. And let's just see if this state of things builds. And it does. That's awesome. So let's just take a moment to check out the state of the code. Let's clear out everything. Let's open the relevant files, task.hpp. And so so over here, we can see our broken attempt at the ETL pool right there. So we can even see both broken attempts. What I will really want to do is just simply bring this thing back, the std array. But before I do that, I don't like the build. My clang D is a bit finicky, but okay, yeah, the build is working, so let's just keep it that way. What I want to do is I want to add my ETL patch, and I'm going to let's take a look at the ETL list. And so you can see the ETL list has the same thing, where it has the ETL list and the ETL I list. And maybe even before the patch, let's see what it would look like. And so right, so even before we do any of that, let me just, so declare remove smart pointer from task, make it a raw pointer. And so let's just take a couple. So this thing, task stack unique pointer. This is just going to become task stack pointer. Or even a reference. Would that be cool? That would be cool. I'm gonna yeah, let's do that. Let's go ahead and make that a reference. There's no move anymore. And empty task. Task, it's going to be this. It's going to have a reference to a task stack. Task stack. Right, okay. No, wait, but it's M. Okay. Oh, but it's, okay, this is sorry, this is confusing. It's a struct, so I'm not using the M thing, so this is just task stack. And so now the task takes a reference to a task stack, which is like pretty cool. And then over here, what we're gonna do is, instead of this thing, we are going to get a pointer here's the part we're going to sort of modify. Rather than this is going to be gone. We're not going to have the pool. We are actually, this is a little bit unfortunate. So place back. So there are a couple options. The main problem is that we want to construct the task with a pointer to the stack, but we can only get its stack once we know the index of the task, which we only get after this thing. So that's a little bit unfortunate. So even here, there's options. There's even options for how to proceed. What kind of patch do we want to make? One, we could, I mean, the stupidest version of this is then we have a setter. And so, and then we do something like auto index, it's like m tasks index of something. This is approximately the API we are going to add, and then p stack equals m task stacks index, and then task.set stack, something like this is approximately how this yeah, what's up, yo, on essence. At first I read the title as day 124. Oh, nice, one's been consistent until I reread the title. Thank you, man. I mean, yep, it is definitely not days, but weeks are a little bit easier to pull off for me. So it is weeks indeed. So this is conceptually the idea. It's like we haven't implemented this yet, but we get a task, we find some way to get its index, we use the index to index into the other storage for the stacks, and then we associate the task with the stack. But this has a lot of problems, because it completely breaks the nice implementation we had where on construction of a task, it initializes the top of the stack with a landing pad. And also that's used to initialize the RSP. And so this is really not the preferred way to do this. It's weird. It requires mutating the task after constructing it. It is not my preferred way. And so the other alternative, add some index of API. The more preferred alternative I'm thinking is adding some API where you can query a list to see what would be the index of the next thing that is allocated. And what that would allow us to do is over here, it would look more like this. And so it's like, okay, we get it's like index of next sort of thing. And then we can use the index to get the p stack, and then we can pass the p stack into here, and then all this goes away. And so then it looks more like this. So this goes away, and we can just kind of up front get the index, get the stack, and then we can just nicely retain our whole system where the task, as part of its construction, it sets up the stack. So What's up, King Too Tall Sensei? Are you thinking of this as a min heap or just linear search? And let me see. Min heap or linear search. What I'm thinking is in order to implement this, I think this will be pretty easy because ETL uses a free list. Or wait. ETL, yeah, I think ETL uses internally, the list is backed by a pool. Oh, okay, so maybe that is a little bit tricky, but internally, there is some kind of linked list that's used to keep a free list of the elements in the linked list. Maybe it's a little bit meta, but for this kind of linked list, it's a static list, and so all of the objects are allocated up front, and so they're like sort of right here, and the list is sort of like a wrapper over this, and then when you go to add a new element to the linked list, it goes to the pool, which backs the whole thing, and then allocates something from the pool. And in order to do that, the pool looks at its internal free list and finds the first one. And so once I have the pointer to, let's say this one is free, I can then do a subtraction from the start of the static blocks to compute the index. Yo, King Too Tall, what? Not a Linux kernel guy, but all OS work is interesting. Hey chat, what is up, King? So for the record, this is not Linux kernel. This is custom kernel. So yeah. It's really not chasing. So it's really just the idea is to find it's sort of like internal indexes. This is sort of a weird API. Internal index of next. And the internal index, like this thing can be pointing to this thing, and then this thing can be pointing to this thing. And this thing can be pointing over here. That's like how a linked list can work. And even though this is at sort of index 1 in the list because it's the second element, for the purposes of allocating and associating and finding its corresponding stack, it is actually at index 2 because I want this kind of one-to-one mapping lined up between tasks and their stacks. And so it's not really the index in the list per se, it's the internal index into the internal storage, which again is sort of a weird API to offer, but that's kind of what I'm thinking. So internal index of next allocated, something like that. Internal index of next allocated. And so this is actually, I think, a bit of a nicer design. It'll allow us to upfront locate the task stack and then pass that into the constructor and even dereference it. And so we can use this pointer or this reference thing even. So running out of time, but let's try to figure out how this might work. So for the moment, just to keep this compiling, I'm just gonna set this to null pointer. This thing. Okay, I'm gonna set this, again, this is just to get it to compile. So it's not gonna run, but it will compile, I think. Doesn't even compile, but okay, I see. MP. Oh, there's other places where I'm using this, but let's see how. I think actually the way I want to do this is I want to develop this in a unit test so I can play with the list better. So let me go find a unit test. I did this last stream. It's kind of nice. So I'm going to go take a unit test. I'm going to duplicate it. ETL test.cpp. I'm going to so what do I need? I need include list.h. Let's see if I can. Oh, what the hell? Okay. Check. Yeah, let's just see if we can compile this. And then we'll right. This thing goes away, this thing goes away. And kernel lib cmake lists copy name, and I'll just add over here. So now I have my unit test and I want to build the host, which, oh no, what? No way. Is the currency make list ETL? So I just need to, oh, hopefully it's as simple as this. So I can just link ETL, please. Oh, damn. Okay, I didn't know. Okay, I did not know that I did not have ETL support in the unit tests yet. All right, I'm gonna have Claude help me debug that. I'm trying to use ETL in a unit test for the first time. Also, I'm trying to use a better model. I guess I only have models for poor people. So, this is the sort of thing that AI is just so good at and would not be valuable for me to try to do. Oh, we got a Twitch chatter. What is up, Metallic Soul? Love it, was still worked on my own for a bit ago and see. Awesome. Thanks for popping in. It's a fun hobby. It's a fun thing to do. While it's cooking on that, let's speaking in parallel. Oh, okay, okay. It stashed some stuff. Okay, I want us to pop the stash. While that is working on the build, we can try to, but it already figured it out maybe. Awesome, this is so great. Right, so so ETL was conditionally linking against the freestanding C headers. And that only is okay if we're building the standalone kernel. But if we're ever doing unit tests, we don't want to use the freestanding C headers. We want to use the systems. So this would be so cool if it built. That's freaking awesome. Dude, AI is so cool sometimes. And I hope I don't get any vibe coder allegations because I just used AI to help me fix a subtle build issue. But that was truly so helpful. So that is going to allow us to go over here and we can do this, and we can even make. You can even see the tests fail. Good. So we're in business, and so now the idea is we're going to do some dev work on the ETL library itself and expose some kind of API called internal index of next allocated. And that name is subject to improvement later. But auto. It is, I mean, to be clear, it is kind of a code smell. No worries, King. No worries for babbling. That's what the chat's for. As a tool, you need to understand it. Way different from making this or that. Yeah. That's what I'm trying to get across. I get some vibe coder allegations every once in a while. So, yeah. To be clear, it is sort of a code smell to have this API. But I genuinely think it is a really nice solution for us. Like, I genuinely think that the internal index of is sort of a cleaner name, but the code is just like more whack. A third option that is possible, and that has not been discussed before, is, or no, scheduler. So instead of doing it this way with this, frankly, kind of strange API, yet another option is we do something like, I don't really know. The idea is we allocate something, some dummy thing from the list, then we can use the index and pass in this thing, and then we can get the stack, and then mtasks dot either destroy, we destroy it, and then we then we like actually create the task with the full thing, and we hope and sort of assume that it's going to be in the exact same space as the thing that we just freed. Which, frankly, I don't really love that either. You could also keep the min index off to the side and change it on task destruction. Just wanted to ask, do you create any hardware at all? I do both. Say, crazy because I love writing drivers. Do you create any hardware at all? So in my day job, I work on an embedded device, but more from a software point of view. Yeah, so just for completeness, I'm going to record this as an option. This is sort of a weird option. It's not immediately clear. That's better. Alloc, get the index free, then really alloc. So it's just decisions all the way down. And so is offering this API a code smell? Internal index of next allocated. Yeah, thank you, man. Yeah, it is a cool job. I do enjoy it. This, I feel like the one saving grace, like the one argument you can make is that this is not a normal linked list. It is a static list. And so kind of being curious about the internal index feels like a kind of reasonable thing to do. Maybe there is something cleaner, but I'm not really seeing it. So, I mean, there's also, maybe it's just a matter of naming. If there's a cleaner name that would make it look a bit more palatable. But this is such a specific thing to ask for that I don't really know. Yeah, that's the tricky part is like, either we do it this way and then have this weird mutation, or we do it this way and don't have the weird mutation and it's very clean. It's more like this. All right, I'm gonna kill the palm tree because I need to go kind of soon. So this is sort of looks like it's much more clean in that we just in place back and then this whole thing constructs. I really do like that, which requires having the stack, knowing the stack ahead of time, which requires knowing the index ahead of time. Then there's this sort of weird thing where you like allocate, get the index, free it, and reallocate. That's also quite ugly in a certain way too. So it's always like, what's the least evil solution here? I think this is the least evil solution. It just is a weird name, but it's not. think it's not necessarily an unreasonable API. So let's just freaking do it. Okay, so we're gonna go to over here. So let's check out the ETL list first of all. So I think in the similar fashion to the ETL pool with this I thing, I think a lot of the implementation is going to be in the parent class in the I list. But here we can see the underlying pool that implements the list, which is pretty cool. And that's what I'm talking about. And so what we want to do, and so ETL is using its own pool as the container for the list nodes. And it's using this data node T type, which subclasses the node T, which is what actually has the pointers to the next and previous. So these are the nodes that are stored in the pool. And that's kind of it. And interestingly, we're still over here. Let me see. So there's no ilist.h. Interesting. So so Victor, honestly, I have no idea what size monitor this is. I don't have a lot of opinions about display setups. I have my laptop over here on the left. I have the main one over here on the right. I think crazy amounts of monitors is sort of over-engineered for a lot of cases, but I'm also not really so into like tricking out my desk setup and whatever. So, all right. Let's see. So basically, I think this method is going to be wow, where's the ilist? Here's the ilist. So the very, very rough sketch of this method is going to be something along the lines of we need to locate the pointer to the next allocated slot. We need to locate the pointer to the start of the pool. We need to know the size of each slot in case it's padded. Then we do a subtraction. That's really the main concept here. And so the first question is, yeah, dang, I'm running out of time. I need to go. So this ilist class is very interesting. This is what has the data node. But, and here is an iterator. Okay. Const iterator, don't care. Here just a bunch of methods, and we would like, it would be really interesting to see in place back, because this is the thing that is going to be involved with allocating nodes, right? So what's up Yas? What's the name of the OS? I don't know. There's no name. naming is kind of the least important part of the OS, so I haven't given that much thought. But someday we'll choose a name. Offline Mark OS. Maybe it's a bit of a mouthful. Right, so we can clearly see we get the P node pool. So we have the pointer to the pool. So that's the first thing we need. So we've got the pool pointer. Then we need to find out wow. Okay, this is sort of... We're getting into the internals of ETL, which is a very interesting library, but kind of foreign. This is sort of weird. You allocate something, get a function pointer, which you need to call or something like that. That's kind of bizarre, but let me take some screenshots. So anyway, the way this works is that it allocates this node, it constructs the data node is like the full thing with the pointers and the value, constructs it into the value. Yep. Insert node. Right, then it uses this internal insert API. Oh. All right, dang, I'm sheesh, yeah. I wonder if my friends are watching this. Like, I need to go meet with some friends in a couple minutes, and they know that I stream. So if y'all are watching, drop a follow, drop a comment in the stream, guys. Yeah, this is interesting. I'm sure there's some way to do it. If it is really way too hard and that would influence this earlier decision, and maybe we have to go back to one of these things, but I was hoping that this wouldn't be incredibly complicated. All right, let's just YOLO this a little bit. So is size t internal index of next allocated. So we can see a couple of things. So we want to get, I'm just sort of recoding this. Let's look at destroy. Perfect. Wait, okay, so we allocate a node just to get the index, and sheesh, I gotta go. So we got the pool, we make sure there is something there. We allocate a node, and I mean, is it really just like p data node? Something like, I think the AI sort of knows what I want to do. Yeah, it's approximately this, but I think it's even data node. Sheesh. P node pool. That's the thing. The P node pool is already basically this thing. Is it sort of like this simple? Probably not. It's approximately, we have a pointer to a data node. We have a pointer to the pool. But this is not totally right because we need really a pointer to the start of the underlying container, which we actually have. It's here. It's the P buffer thing, which is not public. This doesn't work because it's not public, but conceptually, the P buffer, and then we need to data node T, something along the lines of this. Like, I think this is approximately what it's gonna look like. We allocate something, we get its pointer, we compute the subtraction between the start of the buffer, cast it to the type, and to let the pointer arithmetic do its thing. We destroy the node, and then we return the index. This does not compile because of this critical piece right here, but maybe I can actually just do something really unhinged and comment out the protection keywords. Which makes all this stuff public now, which makes this thing legit, which makes does this compile now? No. And that's, yeah, so I sort of don't, I thought I was putting this in the right place. Ah, I misspelled it, is that right? Whoa, okay, let's try. Okay. Okay, that compiled. Yeah, let's just go. So okay, this failed. But that passed. Okay, and then now let's my list dot emplace back 42. 42. And then now let's check if this is 1. And this passes, right? I think it works. I gotta go. I'm late. I gotta go. But I think you see we had the list there. We emplaced one thing into the start of the list, so the next internal index should be 2. Should be 1, and that's what it says. And if we list dot okay, I don't know. I gotta go. I gotta go. But that's the general concept. I think it sort of even worked. And then so now we can access the internal index of the next allocated thing, and then use that for the task stacks later. So I'm just gonna say thank you very much for joining the stream. I do need to leave. I'll see you next week. If you're enjoying the content, smash the subscribe button, and I will see you later. Peace. All right, have a great week. I'll catch you later. Peace.